Okay.
Hello. We can hear you okay. We have your presentation started, so just let us know when we need to move on. Thank you.
Right. Thanks very much. So thanks for giving us the time to present this proposal, and look forward to running through our plans for the Comet Interceptor mission that we hope that ESA will select in the near future. So I'm Geraint Jones. I'm the lead, the primary contact with ESA for the proposal, and Colin Snodgrass is co-leading it at the University of Edinburgh in the UK. So next slide, please. So Comet Interceptor is a mission proposed to the European Space Agency in response to a call it had last year. The F-class call is for modest-sized missions. So the cost to ESA at the end of the mission can't be any higher than 150 million euros, but that does not include launch cost, and science instruments are usually not included in this sum. So the ESA member states and other collaborating agencies generally fund the instruments and the science teams. So the constraints on the mission, so everything that's proposed to this are 850 kilograms maximum wet mass. We expect to launch in 2028 with the aerial exoplanet mission, and we'd be delivered to Sun-Earth Lagrange point 2. So in October, for the first phase of the proposals, 23 proposals went in, and then that was down selected to 6 late last year. So Comet Interceptor is one of the 6 shortlisted proposals that will be submitted in March, so only a few weeks away. Next slide, please. So we're targeting a dynamically new comet, or if we're fortunate to find a suitable target, an interstellar object. And we heard from Julie a little earlier about the value of exploring such objects, but I'll just touch on the main drivers again. So previous Comet missions have all been to objects that have passed the Sun many times, being on short period orbits. So targets are relatively evolved with thick dust mantles, but if we go to a dynamically new comet coming in from the Oort cloud, it's probably nearing the Sun for the first time. So we'd encounter a pristine comet, hopefully with surface ices as first laid down at the solar system's formation. Next slide. So just to use a figure from a paper by Jewett, so we have encountered many of these objects. So okay, some of the tick marks aren't appearing in the PDF version, but as we saw earlier today, obviously we've seen objects in the Kuiper belt now, with the great observations a few weeks ago by New Horizons and Pluto before that. We've seen Jupiter family comets, and Halley-type comets as well. But so main belt comets out in the asteroid belt is beyond the range of what we can reach with this F-class call. But long period comets, when they venture in towards 1 AU, that is a type of object we could potentially explore. So next slide. So just go back one. Forward one. I'm sorry. Yeah, I thought you'd gone forward 2 when you actually hadn't. Okay, so the only way to encounter dynamically new comets is to discover it early enough to be able to send a spacecraft to it, as Julie covered earlier on. And the likelihood of this happening will soon be greatly increased by LSST. So as you see from this figure from a very recent paper on the archive, the distance at which comets are being discovered due to new surveys is much further out from the Sun than it used to be. And with LSST, we expect this to increase much further out as well. So we don't expect a significantly larger number of dynamically new comets found every year, but we'll find them at larger distances inbound. So our advantages with this mission is we don't have to launch from the Earth's surface. We'd already be at L2, ready to be sent on to a suitable target if a suitable comet is found with a very high eccentricity or even a hyperbolic trajectory if it's from outside the solar system. Next slide. So as I said, yes, we'd wait at L2 after launch. So at the moment, we're looking at timescales of roughly 2 or 3 years. If we're extremely lucky, we might even find a suitable target before launch. But assuming that we stay at L2, once we've identified a target and that we can reach it with the delta V we have, there'd be a cruise phase and then a fast flyby, roughly 1 AU, give or take a fraction of an AU on either side. So it'd actually be a multiple spacecraft flyby. So there'd be a primary spacecraft A, which would be passing by at a safe distance. That exact distance dependent on the activity of the target, and that would release sub-spacecraft to go closer into the coma. So they'd relay data in real time to the primary spacecraft, as they'd be the higher risk of being lost to dust impacts. So you can see at the bottom just a cartoon showing the different phases of the mission, and after the flyby, we may not have live data during the flyby itself, and we'd send back data after the encounter from the primary spacecraft. Next slide, please. So there are challenges, of course. So as we don't know what the target is going to be, we have to cater for a huge range of different flyby geometries, so relative paths through a coma and past a nucleus, and also if the target is retrograde or an interstellar target, the flyby speeds could be incredibly high. So as mentioned earlier, for the Giotto encounters, these were very high as Halley was retrograde. But we have to plan for this. We might have a flyby speed approaching 80 kilometers a second, and we have to have a mission that can cater for this. So the cost means that the entire mission should be less than 5 years in duration. So the wait at L2 is limited to roughly 3 years. If we don't find a suitable target, then we'd go to a backup short period comet. It wouldn't just be a repeat of previous missions. We do plan to carry out new science at a short period comet. So the next slide covers some of the new science that we would do at either a newly discovered object or a short period one. So we'd carry out multi-point measurements, so in situ measurements, including of the plasma environment, so we can separate spatial and temporal effects. So the Halley encounters, for example, it was just a single measurement along a single line for each of the individual flybys, but with 3 spacecraft traveling through together, we can get a bigger picture of what's going on and separate spatial and temporal effects. One of the instruments we intend to carry would be an energetic neutral atom analyzer, so we'd see the process of charge exchange between solar wind and neutrals in the coma. We'd also have multiple views of the cometary nucleus from remote observations from 3 platforms. That would reveal the 3D structure of the nucleus and coma in a single flyby. And one of the sub-spacecraft is planned to be a spin-stabilized one, and on that we'd have an instrument called ENVIS, which would carry out multispectral mapping of the coma surrounding the spacecraft. So almost 4 pi coverage at different wavelength ranges and polarimetry as well. So we'd have an all-sky view of the dust, including polarimetry, neutral gas and ion features as well. Next slide. So this is just a cartoon showing the approach as we'd be getting close to the target. So we'd judge the flyby distances based on the activity level of the targets, and of course, with a newly discovered object, there may be big uncertainties in its exact position. But we plan to have 2 sub-spacecraft, one led by ESA, labeled B2, and one by hopefully by JAXA. So we're very hopeful that this will be confirmed soon, that JAXA would be providing one of the sub-spacecraft. So they'd be released from the primary spacecraft on approach, and then spacecraft A would carry out a small deflection maneuver to move it further upstream of the nucleus. And then the next slide. So this shows the flyby itself. So we'd have two of the probes much closer to the nucleus, relaying their data in real time to spacecraft A. And so you can see some of the instruments that we plan to carry on the subspacecraft there on the right. Spacecraft A would carry a powerful camera, so it's actually would make use of the flight spare of the Cassis camera on the ExoMars Trace Gas Orbiter. So that would obtain high quality observations of the nucleus from a greater distance. And then after the encounter, the lower left, the main spacecraft would point its high gain antenna to Earth to relay the data back to the ground. And then if the sub-probes survive, then there'd be continued solar wind observations for some period after the encounter as well. So right at the top, there's a note about possible additional CubeSats. So as I'll come back to in a moment, this isn't in the baseline proposal to ESA, but is to be mentioned as an option. So next slide. So here's a team picture from our meeting in London 2 weeks ago. So we've got a very large group already of people interested in cometary science and the instrumentation from all over Europe, also Japan, and as you can see, several institutions in the US as well. And the next slide. So, so for US involvement, as I've just said, there are several US-based scientists already involved in the proposal. So for the proposal we'll be going in March, we're not including a NASA-funded element as part of the baseline mission, but the proposal will make it clear that such a contribution is possible if mass allows. So we'll be using a new launcher, Ariane 6-2, and if its performance is better than the current level, it is expected that it should rise, then that could free up some mass on the mission. So a NASA-funded CubeSat could be proposed in the next couple of years if that opportunity arises. So we're in touch with several groups who are interested in taking advantage of this if the opportunity arises. So it's nearing the end of your meeting, so I'll just briefly point out the Twitter account and the website. So please do feel free to get in touch with Colin and myself with the email addresses at the bottom. You can also find the contact details on the website. And if you just want to express your support for the aims of the mission in general, there's a contact form and registration form on that website too. Okay, thanks very much.
Thank you. Questions? Comments? Yes, online.
So Joel Marks asked, have you considered planetary defense applications?
Joel Marks asked, have you considered planetary defense applications?
Yes, we have. So we've mentioned that in the phase 1 proposal that went in October. So because this is a science-driven proposal, we don't want to overstress it because ESA also has a space safety program as well. So we just want to clearly demarcate the difference between this science-driven proposal and the use of a platform such as this to potentially act as a line of defense against impacts in the future. So we are mentioning it, and yes, we are making it clear, but not stressing it because of our science aims for the primary cause for proposing this.
All right, thank you. Yes.
A question about have they looked into the detection rates for LSC for short period and long period comets? Because right now there are estimates from I think in the mid-2000s, but we haven't had any recent estimates So they looked into what the long period or short period of rate.
Yeah, so the question is from Meg Schwamm, have you looked into what the detection rates for long period and for short period comets by LSST should be?
Yes, we are actually looking into that in great detail. So Michelle Bannister at Queen's University Belfast is working with that on that with Colin Snodgrass. So yes, there are several members of the LSST community on the mission proposal team, and yeah, we are clearly benefiting from the great increase in detection rates and the greater distances at which we'll be finding potential targets as a result of that observatory coming online in the near future.
Any other questions? All right, thank you very much.